Good morning, students. Mr. Carver here. Today we're going to do section 3.5, limits at infinity. But first, we're going to start off with a warm-up problem, or three. All right, so try these two. Why don't you pause, work them, and then I'm going to work them right now. All right, so the first one here, we can rewrite this just slightly. Remember that when the squared sits on the trig function, it is really the same as having the entire trig function squared, including what you're taking the trig function of. So now what we're left with is a product rule, and there's going to be chain within them, because both of them require the chain. So we'll start off with the left one first. My y prime. So if I derive this section here, it is something to the second power, so that 2 comes down to the front. The inside stays the same. All of that is to the first, so I'm done with that. And now I go inside and derive the cosecant. The derivative of the cosecant is the negative cosecant of 4x times the cotangent of 4x. Should be a 4 in there. Let's keep track of what we're doing. Done with the cosecant, and then I multiply that by the derivative of the innermost function, which is 4. I don't want that to be in red. I want that to be in black. That then times the second as is, that is the cotangent of 4x. I'm then going to add to that for the second part of the product rule. I will do the first as is, so let's get rid of this. Now what we're going to do is derive the second part, but I'm going to copy down that first part there, and now I'm going to derive the underlined parts. The cotangent goes to negative cosecant squared of 4x. So again, I'm going to keep track of what I've derived. Derive that, and now I go with the derivative of the innermost function. Again, that's in red. I don't want it to be in red. I want it to be in black. All right. So there's your unsimplified derivative of that original function. All right, let's get rid of this. And let's do the second one. All right, so what I'm looking for, intervals of increase, decrease. Increase, decrease implies slope, which means I need critical numbers. To find critical numbers, I'm going to derive. So I've got f prime of x. I'm going to use the quotient rule. So I've got low d high minus high d low. This is all over the square of the denominator. All right, so I'm going to clean up the top. This is going to give me 2x cubed plus 2x minus 2x cubed. This is all over x squared plus 1, the quantity squared. This, again, is y prime. I want to clean up the top. That gives me 2x over x squared plus 1, the quantity squared. So my critical numbers, again, come from the top and the bottom of the first derivative. So my critical numbers are going to be x equals 0. That's what I get when I solve the top. And the bottom, I only get imaginary numbers. I square root 0, I subtract 1, I take the square root of negative 1. So I get no critical numbers from the bottom here. Now if I'm looking for intervals of increase, decrease, I put them on a number line, all my critical numbers, and I test. I'll do f prime of negative 1, and then f prime of 2. Again, just picking general numbers at random within each of those intervals. I take negative 1, I plug it into my first derivative. That looks like it's going to be less than 0. I take 2 and plug it in. That gives me a positive. That's greater than 0. So my interval of decrease goes from negative infinity to 0. My interval of increase then goes from 0 to infinity. The boundary points are not included. All right, so let's go move on to 3.5. Section 3.5 is limits at infinity, and essentially what we're going to do is we're going to look at the behavior of the graph at the far reaches of the x-axis. So let's say, for instance, that I have a function with a horizontal asymptote of 0. Horizontal asymptotes are, in fact, limits at infinity. It tells you the behavior of what the graph does as you get far, far out onto the x-axis. So you might have a graph that looks something like this. That might look familiar to you. Something like that. The limits at infinity is just behavior right here. It's how it gets closer and closer and closer to 0. That's what we're looking for in this section, and I'm going to show you how to do that right now. All right, now if I take a look at this function here, I don't care about critical numbers. I don't care about vertical asymptotes, anything like that. All I'm looking for in this section is what happens when I get out to the far reaches of the x-axis. So I'm looking at this. This is the limit as x goes to 0. So in this case, we're examining what it does as it heads out to the right. Now think about what you're doing here. You're plugging in gigantic numbers for x. So I think you might agree that if I take 1 trillion, for instance, and I square it and multiply it by 4, the fact that I either add 1 to it or add 6 trillion to it doesn't really matter. It's this term right here that determines the behavior of the top, the numerator. Ditto for the bottom. If I take 1 trillion and I square it and then multiply that by 5, does it really matter if I'm subtracting 11 from it? The answer is no. So you're going to take the most dominant terms in the top and in the bottom, and you're going to say that that original function is roughly equal to 4x squared over 5x squared, because everything else does not really matter at huge, huge values of x. These are going to cancel. They're the same number. The ratio is 4/5, which means as I go out to infinity, let's say this is 1 right here. 4/5 looks like about that. This graph will level out at 4/5, whether it comes from below or whether it comes from above, it will level out at that y value. Whether it comes in from above or below will be told to you by all the other indicators, for instance, the first derivative test and the second derivative test. All we care about is where this thing levels out at. All right, let's clean that and do another. All right, let's say I take a look at this function here. Now I'm going to plug in giant negative numbers, like -1 trillion. And I think, again, using the same argument as I did in the first example, 7x is the main driver of the behavior of the numerator, and x squared is the main driver of the behavior of the denominator. So I could say that this is roughly equal to 7x over x squared, which I could say is equal to, when I cancel those x's, 7 over x. Now remember, here's what's happening. I'm plugging in a giant, giant negative number in for x. So say something like 7 over -1 trillion. 7 divided by a gigantic number is going to get closer and closer and closer to 0. In fact, the bigger x gets, the smaller that fraction gets. So this is going to level out along the x-axis. So here's a couple of rules that you can go with. If they are equally heavy, like for instance, this first one here, when I say equally heavy, I mean that the powers in the numerator and the denominator, are equal. You got an x squared in the top and an x squared at the bottom. The limit is equal to the coefficients in front. So you can see it's 4/5. If it is bottom heavy, like for instance, this second example here, outlined in gray, bottom heavy means the denominator has a higher power than the top. I've got 7x to the first and x squared in the bottom. As you go to infinity or negative infinity, the answer will always be 0 because the bottom, the denominator, outgrows the top of the numerator. All right. Let's take a look at the last possible combination, right? We had equally powerful, we had bottom heavy, and now we're going to look at a top heavy example. So now I'm going to positive infinity. Just like in the last two examples, I'm looking at my most dominant terms in the top and the bottom. That's -4x squared in the top and x in the bottom. So I'm going to say that that is roughly equal to -4x squared all over x. And again, the reason I can do this is because I'm looking just for the general behavior of this graph. The 2 and the -1 make absolutely no difference to the general behavior of this graph. It are the large x values, the most powerful x values, that drive the behavior of this function. I could then say that this is equal to -4x over 1 if I cancel the x's. Now what's happening is I'm plugging in a positive infinity. That looks like a negative, but it's actually positive infinity. So I've got -4 times 1,000,000,000 over 1. This answer is negative infinity, which means as I go out to the right-hand side, it's going to get bigger, and it's going to get to be a bigger and bigger negative number. It's going to dive off to the right. Let's say I go the other way. I'm going to use exactly the same function. Now, what if I take the limit as x goes to negative infinity? Again, I can still say that this is roughly equal to negative 4x squared over x. And when I cancel, I get negative 4x over 1. I plug in a giant negative number. Let's say negative 1 billion times negative 4 gives me a huge positive number. So the limit on this one will be positive infinity. All right. Now, some of these get to be a little confusing. Let's take a look at this one. If I take the limit as x goes to infinity, let's do the square root of 4x. All right, the square root of 4x squared plus x plus 1 all over x going to positive infinity. I'm going to use the similar argument. These are the most dominant terms in the top and the bottom. So this is going to be roughly equal to the square root of 4x squared all over x. So I can simplify the top a little bit. I square root the 4, that gives me a 2. And I square root x squared. So here's a rule that you need to remember in this class. If you undo an even power, you always get the absolute value of that thing. For instance, you don't need to write this down, just check this out. Let's say I've got x squared is equal to 4. If I square root both sides, I end up getting the absolute value of x is equal to 2, which means I get x is equal to 2 and x is equal to negative 2. It's this middle step right in here that I want to call your attention to. If I undo an even power, I always get the absolute value of it. Now, for solving it's important, but for limits it's really important. So let me get rid of this. And we're going to go back up to my example. So this gives me the square root of 4 of 2, and then the square root of x squared, which is going to give me the absolute value of x over x. Now, this is kind of like taking limits in the special case from way back in chapter 1. But if I plug in a trillion into the top and in the bottom, I get 2 times a trillion over a trillion. Those are going to cancel to give me 2. Now let's go off the other way, because this is where it changes just slightly. So now I'm going to go to negative infinity. I'm still going to pick up right here. This is equal to the square root of 4x squared all over x, which is equal to 2 times the absolute value of x over x. Now it gets a little different here, because if I plug in negative 1 trillion into the top and the bottom, the absolute value in the top will make it positive, yet these still do cancel, but they cancel now to negative 1. So this is going to give me negative 2 for an answer. So this looks a little strange. It does all kinds of weird things. It's got a vertical asymptote at 0. And again, all of that stuff will be clear once we start testing everything, first and second derivatives. But for right now, suffice it to say that if you go out to the right, this thing is going to level out at 2. And if you go off to the left, this thing will level out at negative 2, something like this. And I don't know that it's concave up or down because I haven't tested that, but that's essentially what's happening. It's leveling off at 2 and negative 2 depending on the way that you go. All right, let's do some trigonometry. Let's take the limit as x goes to infinity of the cosine of 1 over x. All right, if I take a look at this and x grows infinitely large, the innards right here, this expression right here is 1 over a gigantic number, which means this expression is roughly equal to the cosine of 0. I think you would agree that as x gets larger and larger, 1 divided by that large number gets smaller and smaller and smaller. That's essentially 1 over huge, which goes to 0. So the cosine of 0 is 1. Ditto if I go the other way. If I take the limit as x goes to negative infinity. I think you would agree that this is 1 over negative 1 trillion, still driving that inner function, this portion right here, to 0. This is the cosine then of 0. Still turns out to be 1. All right, how about something like this? Let's take the limit as x goes to hugeness of the sine of x over x. Now, some of you may be thinking that this goes to 1. That was an identity way back from chapter 1. The reason this isn't going to be 1 is because this is not indeterminate. If you plug in infinity into the sine of x, think about what happens to the sine curve, right? The sine curve looks something like this. And as I go to infinity, just of the numerator, I think you might agree that the top is just plus or minus 1. The top does not grow. It just bounces back and forth between plus and minus 1, while the bottom continues to grow bigger and bigger and bigger. Plus and minus 1 divided by a huge number goes to 0. So in this case, it is a bottom-heavy fraction. The sine does not grow while the x does grow. That limit is 0. Ditto, by the way, if you go to negative infinity. Plus and minus 1 divided by a huge negative number is also 0. All right, let's take a look at this. Thinking about the most dominant terms in the top and the bottom, the cosine does not grow. The cosine just oscillates between plus and minus 1, while the x's get big, big, big. So the two most dominant terms are x in the top and x in the denominator. This is then roughly equal to x over x, which reduces to 1. And it doesn't matter if I go to positive infinity or negative infinity, they are both going to cancel to positive 1. All right. All right, this isn't trig related, but let's just say I go to infinity of this function right here, 3 plus 4 over x. There is a property of limits that says if you have the limit of a sum, it is equal to the sum of the limits. So I can break this up and just limit each one individually. This first part here, 3 does not grow. It doesn't matter how far you go out into the x-axis, rather. That is just 3. Plus the limit of 4 over x as x gets huge. That is 0. The answer is just 3. You can get the same thing working from the original here. At huge values of x, this just goes to 3 plus 0, giving you the same answer. All right, guys, that should be enough to get you through. I'll see you later in class and answer any questions that you might have. Thanks much.